Okay, so the last time that we left off, we were basically finishing up talking about empirical methods that economists use to try to estimate the effects of policies. And the one thing that I haven't really covered yet, which we need to talk about, is the issue of statistical significance. So just because you find that there's some non-zero correlation in the data doesn't mean that there's necessarily a true relationship between the two variables that you're looking at, because of course it could be the case that there's some correlation in the data, but it's basically just due to statistical noise. And I mean, this is no different than thinking about, say, like polling results right now, right? So if you see a poll that has Obama up by, say, 3 percentage points over Romney, you'd probably say, well, the difference, the 3 percentage point difference, is within the margin of error of the poll. And what that's saying is basically that the poll is drawing us random sample, or hopefully a random sample from the larger U.S. population. And what you'd like to know is, for every single person in the population, how would they vote? Would they vote for Obama or would they vote for Romney? But of course, it's, sort of in terms of the economic resources that would be required to actually poll every single person, it would be absurd. So what you do is you instead take a smaller sample of the population and see what proportion of them are going to vote for Romney versus what proportion are going to vote for Obama. And whether or not, you found this margin for Obama, but whether or not that margin represents that Obama truly leads in the overall population, or it just represents that there's some sampling error because you have a finite sample that doesn't cover the entire population, is basically a question of whether or not that difference is statistically significant. So that's so sort of this type of sampling error that we're concerned about when we talk about statistical significance. And so we can imagine that even if we have this equation that y is equal to beta naught plus beta 1 xi plus EIT, we can imagine a case in which the true population beta 1 is equal to 0, but in some finite sample, beta 1 is not going to be exactly equal to 0. So even if there's no true relationship between x and y, which is when we say the true relationship, we basically mean what coefficient would we estimate if we had an arbitrarily large or infinitely sized sample. So even if there's no true relationship between those two variables, in a specific sample, there might be some sort of relationship between them. And so determining or figuring out whether or not the estimate of beta 1 that we have represents a true relationship or statistical noise is basically the goal of talking about or figuring out statistical significance. So it turns out that using statistical theory, we're able to derive the distribution of that coefficient beta 1 that we're interested in estimating under the assumption that the true coefficient is 0. So basically what we're going to do here is we're going to say, well, let's suppose that it is the case that the true coefficient beta 1 is equal to 0. Under that assumption, it turns out we can basically figure out what the sampling distribution of our estimate of beta 1 is going to be. So basically sort of like what confidence interval or how much dispersion there might be in that estimate of beta 1 around its true value of 0. And once we know that, then we can look at the actual estimate of beta 1 that we got and compare it to the sampling distribution that we derive under the assumption that beta 1 is equal to 0. And if we find that our actual estimate is way outside that sampling distribution, then what that's going to tell us is that basically the assumptions that we used to derive this distribution are wrong. And in particular, we're going to conclude that the assumption that the true beta 1 is equal to 0 is wrong. And so then we're going to reject that hypothesis that beta 1 is equal to 0 and conclude that the true beta 1 is actually something that's either greater than or less than 0, depending on whether or not our estimate of beta 1 is positive or negative. So using statistical theory, we can basically express how unlikely it was that we'd find an estimate of beta 1 as large as the one we observed under the assumption that the true beta 1 is in fact equal to 0, which is the hypothesis that we're going to be interested in testing. So we're sort of going to come in and say, well, let's assume there's no true relationship between these variables. And under that assumption, how likely is it that we would estimate a beta 1 that was as large as the one we actually observed? So one thing that is I think really important to emphasize here is that this question of statistical significance is sort of independent or unrelated to the question of whether or not your estimate of beta 1 is unbiased. So the question of whether or not your estimate of beta 1 is unbiased is basically a question of, if we had an infinitely large sample so that our estimator had pretty much zero statistical noise, it converged perfectly to what the true coefficient value was, or at least what in expectation that estimator should converge to. So if an estimator is biased, basically what we're saying is that even in an arbitrarily large sample, the value that you get for, say, that coefficient is going to be different than the true causal effect of x on y, right? Alternatively, if we say that we're asking whether or not something is statistically significant, we're basically asking how close is this estimator to its true value, or what it would be if we had an infinitely large sample. And so an estimator could sort of, you're basically quantifying the amount of noise. So I guess, again, if you want to think in terms of like polling, since that's something that's going on now, so bias in polling, the question of whether or not you have a bias poll would basically come down to whether or not you're actually getting a random sample of people, right? So a poll could be biased if, for example, you could only telephone landlines and you couldn't telephone cell phone users, right? So in that case, what's going to happen is that instead of getting a random sample of the entire population, you're going to get a random sample of landline users, but landline users are going to be different on average from cell phone users. Like a cell phone user probably tend to be younger, maybe they'd be more likely to be students, or maybe less likely, I don't know. They might have sort of below average or above average incomes. But all of these, there's all these sort of factors that could be related to how they vote. And so if you're only getting a random sample of landline users and not a random sample of cell phone users as well, then even if you can make your sample arbitrarily large, right? Even if you could sample every single landline user in the United States, you'd have a really, really precise estimate, but it would still be biased. It wouldn't tell you how the overall population is going to vote because it's missing this entire segment of the population, which are the cell phone users, right? So that would be a case where you basically had a very statistically significant coefficient, at least in the sense that you have a very precise estimate, but the estimate itself would still be biased. The alternate sort of possibility, or the problem of statistical significance, is different than the problem of bias. So you could have a random sample of the U.S. population, but if that random sample only contains like say 10 people, then it's very unlikely that it's going to give you a, well, I don't want to say statistically significant estimate of the vote share for Obama, because statistical significance refers to the statistical significance of a particular hypothesis. But let's say that your hypothesis is that Obama is going to win if the vote were held today, right? So you could then test that hypothesis basically using polling data. And if you had a random sample of 10 people in the population, it's very unlikely you would be able to achieve statistical significance when testing that hypothesis, right? Because who knows? The random sample of 10 people, you could get all 10 voting for Romney or all 10 voting for Obama. It's not that hard to imagine. So this issue of bias and this issue of statistical significance are two separate things that you want to think about. So the rule of thumb for statistical significance turns out to be, what we do is we calculate this thing called the t-ratio, which I'll discuss in a moment, and then we determine whether or not that t-ratio exceeds 2 in absolute value. So conveniently enough, it turns out that under most circumstances, the sampling distribution of the coefficient beta 1, the thing that you're estimating in your regression, is going to be approximately normal. And in particular, it turns out that if you take that coefficient and you divide it by its standard error, which the regression will give you using a formula that you don't really need to know, but it's there, that ratio of those two things is going to be distributed approximately normal with a mean 0 and a variance 1. So it actually follows something that we call the t-distribution, but for any sufficiently large sample, which is like anything over 20 or 30 observations, the t-distribution pretty much looks similar to a standard normal distribution, which is a normal that's centered around 0 and has a variance of 1. So if the true beta 1 is equal to 0, then under that assumption, this thing that we're looking at, this ratio of the estimated coefficient divided by its standard error, is distributed approximately normal 0, 1. And so if you remember anything from statistics, hopefully you remember that the value or the probability of observing a standard normal random variable being greater than 1.96 or less than minus 1.96 is 5%. So that's what we call like the 95% or the 5% critical value, depending on where you're, which direction you're looking from or which perspective you're looking from. But all we're saying is that if we have some random variable x, which in this case would be equal to beta 1 hat divided by the standard error of beta 1 hat, this thing we're saying is distributed pretty much like a standard normal random variable under the assumption that the true beta 1 is equal to 0. And so if that's the case, then we know we have this sort of bell-shaped curve that gives you the distribution. This is 1, 2, minus 1, and minus 2. So we're saying that if it has this distribution, then the probability that you're going to observe a value for that random variable that's either greater than 2 or greater than 1.96 and less than minus 2 or less than minus 1.96, the total probability mass in each of those tails summed together is equal to 5%. So there's basically a 1 in 20 chance that you would observe some value of the variable that was sort of more extreme than plus 2 or more extreme than minus 2. So if we observe that, then so if we observe that our estimate of beta 1 is, or its t ratio rather, is greater than 2 in absolute value, we say that beta 1 is statistically significant at the 5% level. So what we mean is that under the null hypothesis, the true beta 1 is equal to 0. There's only a 5% chance or less that we would observe the estimate of beta 1 that was as large as we in fact saw. So that's only a 1 in 20 chance, which seems like pretty low, all things considered. And so since that seems pretty unlikely, we reject the hypothesis that the true beta 1 is equal to 0, and we conclude that there is a true relationship between x and y. So in terms of how one might, sort of think about statistical significance in a real world scenario, last year when I taught this class and we were talking about statistical significance, sort of by coincidence, I think, Steve Jobs died, I don't know, within like a day or two after the lecture that we had where we started to discuss statistical significance. And the timing of his death was sort of was more coincidental in the sense that it turned out like Apple announced the next iPhone the day before he died, and then the next day it turned out that he had died. And so the question that I posed to the class then, which I want you guys to think about as well, is basically if you were to think about testing the statistical. So what we observe is that they release the iPhone, and then the next day he dies, right? And so let's have as our sort of null hypothesis, or the hypothesis that we want to test, that those two events are unrelated. So let's in particular presume that the timing of the release of the iPhone is sort of more or less random. I mean, it's not truly random. You can always tell that it's like somewhere in the summer or the fall. But we can at least assume that it's kind of random with respect to when people tend to die, right? Because people basically sort of tend to die evenly throughout the year, and they're just releasing it in some particular time frame that's sort of like sometime during the summer to the fall. So let's assume that sort of when people die is basically random with respect to the iPhone's release, and vice versa, that the iPhone's release is random with respect to when people tend to pass away. So under that hypothesis, what's the probability that we would have observed the actual outcome that we in fact observed, right? So what we actually observe is that he dies the day after the iPhone is released. So if we think that those two events are completely unrelated, what's the chance we would have observed that actual outcome in the data? And given that chance, what would you conclude that basically would you reject the hypothesis that those two events are unrelated? Would you conclude that in fact there's a statistically significant relationship there, or would you say that no, I don't think that they're basically I do think that they're unrelated. I don't think that there's some causal mechanism going on there, and I can't reject the hypothesis that they're basically that it was just random. So the questions, just to be clear, are so it's going to be what's the probability that you would pass away within a day of Apple releasing the iPhone if the events are unrelated. And so I need to kind of put some sort of bound on here. So let's say, and okay, so let's suppose that everybody knew that he was sick. Let's suppose the doctors were like, well, we don't know exactly how long he's going to last, but he's going to die sometime in 2011, and basically, we think it's going to be pretty much a random date. So under the assumption that he would die with equal probability on any date in 2011, and that his death is going to be unrelated to the release of the iPhone, so it's not like he's just sort of like waiting for the iPhone to get released and then just being like, okay, well, that's it, like I'm done here. Then what was the probability of this occurring? So that's the first question, and then the second question is, do you reject or accept the hypothesis that the two events are unrelated? At the 5% level. Okay, so why don't you guys just talk in your groups for a few minutes to figure out what it is that, what your conclusions are on these two questions, and then I'll, as usual, probably randomly select a group, unless the group wants to volunteer, in which case you'll be free to do so. Huh? You can go either way. If you want to include the same day, that's fine. If you don't want to, then that's fine too. So I'll accept either of those answers. Yeah. So the in 2011. Yeah. I mean, obviously it's kind of arbitrary that why would December 31st, 2011 be somehow much more likely than January 1st, 2012 or something like that. But just to make the problem more tractable, let's assume that they're like, we know it's going to die sometime this year and it'll be one of these days, sort of all equal probability, but we don't know which one.
And should we also assume that the iPhone release date has already been set?
Yeah, you can. So it doesn't, like, if you want to think about Apple sort of in 2010 already knew they were going to release it on like October whatever 2011, that's fine. On the other hand, if you want to sort of view it as being like a random process that like they don't know exactly when, it's going to depend on the manufacturing constraints and stuff, that's fine too. Lexi? Oh, on the bottom there? Sorry, that's standard error. But you don't know. You can't really use that equation to. Yeah. Okay, I'm going to have you guys wrap up in the next like 60 seconds. Okay, is there a group that wants to volunteer to answer? Okay, group 6 wants to volunteer.
So for one, because you said within a day of releasing the iPhone, I could basically be a day before and after, so it's like 2 out of 365. Mm-hmm.
Sure. Yeah, so that would be like basically 1 over 180 pretty much.
Yeah. So pretty insignificant. And
well, did you say insignificant or? Well, okay, so then what's your answer to question 2 in that case? Do you sort of reject or accept the hypothesis that those two events are unrelated at the 5% significance level?
I think I accept that they're unrelated.
Well, okay, so why would you conclude that?
It was just kind of hard to remember that work. It was like, you can't test it again. It's data one day.
Well, okay, but you have, so you sort of, in some sense you build up like a model of the world, right, that says that he's going to die sometime this year, they're going to release the iPhone sometime this year. I believe those events are unrelated, and you just told me the probability, given that model of the world, so those 3 things, right, you told me correctly that the probability that he's going to die within a day of them releasing the iPhone is basically 1 in 200, right? And then you actually observe that happening. So does that make you like more or less confident of the model that you just built up? Lexi? Right. Yes. So basically, like what you've done is you like built this model, and then you said, well, under this model, I just observed this event. The probability of observing this event was less than 1 in 100. That's that's pretty unlikely. So I guess if you like go to Vegas and believe that you get really lucky or something, then maybe you'd be like, oh, I'm not like that surprised that I observed an event that had only a 1 in 200 chance of occurring. But I think under normal circumstances, you'd be like, well, that was really unlikely. That should make me sort of question the model that I built up. And in particular, the hypothesis or the link that we're really questioning in this model is the assertion that those 2 events are unrelated. So if instead the alternate model is that in fact they're related and that he was kind of like waiting until the iPhone got released and was like, I really want to see it through and like see them release the next model, and then after that it's kind of like, okay, well, now it's like the end of it. So under that. Under that alternate model, the event that you just observed is much more likely to occur than under the assumption that they're completely unrelated. Now, I guess if another group wants to do sort of have a bonus question, what if we change this? Did you have just a general question?
Yeah, just going back to the probability. So 50% of 2 and like 200, saying that the probability is definitely like 5%, so that's why we got the significance.
Right.
I think that's probably where at least my confused on because of the T ratio and then kind of skipping a step in
right.
part.
Yeah.
I was thinking, okay, it's definitely going to be less than 2 in absolute value, but that's not the T ratio.
Yeah. Yeah, so that's a very good question. And so you're absolutely right that like the rule of thumb that I gave you up here, and this basically what comes down to is like the statistical distribution that we're talking about right here is not the same as the distribution that you're calculating here. So the T ratio is basically itself, and it's what we call a statistic, which basically just means it's a quantity that's calculated from the data, and then we know it follows a particular distribution under our hypotheses, and so we know what values are sort of unlikely to appear and what values are more likely to appear. And so when I say that the rule of thumb is whether T is greater than 2, I'm just saying that if you have this thing that's distributed like the T statistic, which is what the coefficient divided by standard error is, then values of greater than 2 in absolute value are very unlikely to appear. And in particular, there's a less than 5% chance that you would observe those values under the hypothesis that the true coefficient is equal to 0. So the link here would be that basically when you get to the step where you say there's a, so I think it was like 1 over 180, so it's basically like a 0.5% chance that we would observe this particular event. What you're comparing is whether